At 1:01 in the morning, local time on August 3rd, 2026, the ground near Sánchez in the Samana province of the Dominican Republic shook with a magnitude 4. 5 earthquake at a depth of roughly 10 to 15 kilometers, according to seismological monitoring from the Autonomous University of Santo Domingo. The tremor was felt across the entire Samana Peninsula in Nagua, the northeast region, Bajo Yuna, and as far away as Santo Domingo. No casualties or structural damage were reported. That earthquake is just one piece of what's actually happening across the Caribbean region right now, because at the exact same time, tropical waves are marching westward off the coast of Africa, some already pushing rain into the islands, while eyeing the Gulf Coast of the United States for potential development later this week. A massive plume of Saharan dust has crossed thousands of miles of open Atlantic Ocean and settled directly over the northeastern Caribbean, dragging down air quality from Puerto Rico to Grenada, and the ground across the wider region has been shaking on and off for weeks. 3 separate natural systems, active simultaneously, all affecting the same people across the same islands at the same time. Here's what's actually happening, explained from the ground up. Start with the tropical weather picture, since that's the one most people are watching most closely this time of year. The National Hurricane Center is currently tracking multiple tropical waves moving across different parts of the Atlantic basin at once. One sits in the eastern Atlantic, still moving westward toward the islands. Another is positioned in the eastern Caribbean, near the longitude of Puerto Rico, pushing southward through the Lesser Antilles. Additional waves are approaching Central America from the east. None of these systems are currently organized enough to be considered a serious tropical cyclone candidate in the immediate term, though some model guidance suggests conditions may become modestly more favorable for development as the month progresses. Tropical waves themselves are worth understanding as a baseline phenomenon, since they're the raw material nearly every Atlantic hurricane eventually forms from, and understanding them makes the rest of this season's forecasting easier to follow. These are elongated areas of lower pressure embedded within the broader belt of easterly trade winds, typically originating over West Africa and drifting westward across the Atlantic roughly every few days throughout the summer and early fall. Most tropical waves never develop into anything more organized than a stretch of showery, unsettled weather passing over the islands they cross, dropping useful rain, and then moving on without ever acquiring a closed circulation. A small fraction, when they encounter sufficiently warm ocean water, low wind shear, and enough atmospheric moisture, begin organizing a closed circulation and can eventually strengthen into a tropical depression, then a tropical storm, and potentially a hurricane. Forecasters track dozens of these waves over the course of a typical season in the process of identifying which ones carry genuine development potential versus which will simply pass. Through as an unremarkable rain event, it is one of the more routine but consequential parts of tropical forecasting during the height of the season, requiring continuous satellite monitoring and model analysis of each individual wave as it crosses the basin. Here's the broader context that explains why this particular August looks so different from recent Caribbean hurricane seasons. The 2026 Atlantic hurricane season is unfolding under the influence of a strengthening El Niño event in the Pacific Ocean, and that single fact is reshaping nearly everything currently happening across the tropics. El Niño is a periodic warming of surface water in the central and eastern equatorial Pacific. When it develops, it reliably reshapes global wind patterns in a very specific and well-documented way. For the Pacific Basin, El Niño tends to act like flipping a switch that turns storm activity up. For the Atlantic, it works in essentially the opposite direction. The warming Pacific waters generate stronger upper-level winds that flow directly across the tropical Atlantic and Caribbean, and those stronger winds, what meteorologists call vertical wind shear, are one of the most reliably destructive forces a developing tropical system can encounter. Wind shear tears the top off developing clusters of thunderstorms, tilts a system's circulation off axis, and prevents the kind of organized vertical structure a tropical storm actually needs in order to strengthen into something more dangerous. This relationship between Pacific and Atlantic storm activity during El Niño years is one of the more consistently reliable patterns in seasonal forecasting, documented across multiple past El Niño events going back decades, which is part of why forecasters place real confidence in this year's below-normal Atlantic outlook, despite the inherent uncertainty involved in any seasonal prediction. Colorado State University's hurricane research team has lowered its 2026 Atlantic hurricane season forecast more than once already this summer as El Niño has strengthened faster than initial forecasts anticipated. Their current outlook calls for a well below normal season, predicting roughly 9 named storms across the entire Atlantic basin for the year, compared to a long-term average of more than 14. NOAA has separately placed roughly a 55% probability on a below normal season overall. The probability of a major hurricane specifically tracking through the Caribbean this year has been estimated at around 35%, compared to a long-term historical average closer to 47%. Those numbers mean the overall threat level facing the Caribbean basin. This particular hurricane season is meaningfully lower than in several recent years, including the extraordinarily active 2025 season, which produced 3 separate Category 5 hurricanes. It's worth understanding exactly how forecasters arrive at numbers like these, rather than simply treating them as an opaque prediction handed down each spring. Seasonal hurricane forecasting relies heavily on analyzing conditions that are already measurable months before the peak of the season arrives. Sea surface temperatures across the tropical Atlantic and Caribbean, the current strength and expected trajectory of any El Niño or La Niña pattern developing in the Pacific, and the broader state of Atlantic wind patterns at multiple altitudes. None of those factors, individually or combined, can predict exactly where or when a specific storm will form. What they can do reasonably well is estimate the overall favorability of the atmosphere for storm development across the season as a whole, which is why these forecasts get expressed as probabilities and ranges rather than specific predictions about individual systems. A below-normal seasonal outlook reflects genuine, measurable atmospheric conditions working against storm formation this year, not simply a guess or a hedge on the part of the forecasters producing it. But lower numbers do not mean zero risk, and they never have. A below-normal seasonal forecast is not the same thing as a no-storm forecast. And right now, the strongest wind shear is concentrated directly across the main development region of the tropical Atlantic and the Caribbean, precisely the zones that historically produce the majority of major hurricanes during the peak months of August, September, and October. A single storm making landfall is genuinely all it takes to turn a quiet statistical season into a catastrophic real-world event for whichever community happens to be in its path. And that is held true in essentially every year of recorded Caribbean hurricane history, regardless of what the seasonal outlook predicted months in advance. 1992's Hurricane Andrew, for instance, formed during a season that was otherwise fairly unremarkable by overall storm count standards. And it remains one of the costliest hurricanes in U.S. history purely because of where it happened to make landfall. Seasonal averages describe an entire basin over several months. They say almost nothing about the specific risk facing any single community on any single day, which is precisely why continued monitoring matters just as much during a quiet season as it does during an active one. The area meteorologists are currently watching most closely for near-term development isn't actually deep in the Caribbean at all. It's along the southeastern coast of the United States, specifically the stretch from northern Florida northward through the Bahamas, South Carolina, and toward North Carolina's Outer Banks. A stalled frontal boundary is sitting in that region right now, a leftover atmospheric feature from a weather system that swept down the east coast and effectively got stuck in place. Moisture has been pooling along that boundary for days, and some model guidance is hinting at a low chance of tropical or subtropical development in that specific area over the coming days. The National Hurricane Center and other forecasting agencies have flagged a low probability for this system, nothing organized or imminent as of this recording, but it's genuinely worth watching. Because this is exactly the kind of nearshore development pattern that has caught coastal communities off guard in recent seasons, when development happens closer to land rather than out in the deep tropics, and where forecasters typically have several days of advance warning. The available lead time for preparation compresses dramatically, sometimes down to less than 48 hours between formation and landfall. Nothing dramatic is expected from this specific system right now, but that particular stretch of coastline bears continued monitoring through the coming weekend regardless. This particular type of frontal boundary development deserves a bit more explanation, since it behaves quite differently from the classic image of a hurricane spinning up from a tropical wave, far out in the open Atlantic. A stalled front is essentially a boundary between two different air masses that has stopped making meaningful forward progress, often because the larger scale steering winds above it have weakened or shifted in a way that leaves it parked over roughly the same stretch of ocean or coastline for an extended period. When that kind of boundary sits over sufficiently warm water for several consecutive days, it can occasionally begin acquiring some tropical or subtropical characteristics, even without a classic tropical wave feeding into it. A process meteorologists sometimes describe as a system transitioning from a purely frontal disturbance into something with a warm core and organized convection closer to what defines a tropical or subtropical depression. These systems tend to be harder to forecast with the same lead time as a wave crossing the open Atlantic, precisely because the ingredients for development can come together somewhat unpredictably along a boundary that's already sitting close to a populated coastline rather than announcing themselves clearly days in advance out over open water. For the Gulf of Mexico and the broader Caribbean Sea further south, the overall picture stays quieter, with the stronger El Niño-driven wind shear keeping most tropical waves from meaningfully organizing as they push westward through the region. The Eastern Pacific Basin, meanwhile, has actually been somewhat more active this year, which is a fairly typical pattern during El Niño summers, when the Pacific side of the hemisphere tends to get energized precisely as the Atlantic side goes quiet. Now to the second major story moving across the Caribbean simultaneously, one that directly affects millions of people right now in ways that have nothing to do with rainfall or storm tracks at all. The Saharan air layer, commonly referred to simply as Saharan dust, is currently sitting over a large portion of the northeastern Caribbean and continuing to move westward toward the greater Antilles, Central America, and eventually parts of the southeastern United States. Saharan dust is exactly what the name suggests. Fine mineral particles lofted high into the atmosphere over the Sahara Desert in North Africa by strong surface winds. Those particles get carried up to altitudes between roughly 5,000 and 15,000 feet, and then transported thousands of miles westward across the Atlantic by the trade wind circulation, typically taking about a week to cross the ocean before reaching the Caribbean, and eventually the Gulf of Mexico and the continental United States. This isn't a rare or unusual event in any sense. It's a recurring seasonal phenomenon that occurs every summer with varying intensity from year to year, typically peaking between June and August before tapering off toward the fall. What makes this particular dust plume significant is how dramatically it's affecting the specific islands it's currently passing over, and how directly it's interacting with the tropical wave activity already moving through the same airspace. Puerto Rico, the U.S. and British Virgin Islands, Anguilla, Saint Martin, Saint Bart's, Antigua and Barbuda, Saint Kitts and Nevis, Montserrat, Guadeloupe, Dominica, Martinique, St. Lucia, and extending southward toward Barbados and the Grenadines are all currently sitting under this same dust layer. That dust is doing two distinct things simultaneously across all of those islands. First, it's dramatically suppressing rainfall by injecting dry, stable air into an atmosphere that would otherwise be gradually moistening in preparation for the arrival of the tropical waves currently crossing the basin. Second, it's degrading air quality to levels that are genuinely unhealthy for people managing respiratory conditions, including asthma, seasonal allergies, and various forms of chronic lung disease. The fine particles that make up this dust stay suspended in the air rather than settling quickly to the ground, which means that breathing outdoor air during a heavy dust event means directly inhaling those particles over an extended period. Health authorities across the Caribbean routinely advise residents to limit outdoor exposure during peak dust events, particularly for children, elderly residents, and anyone managing a pre-existing respiratory condition. Visually, the effect is genuinely striking. The sky takes on a milky, hazy appearance, and the region's normally vivid blue horizon becomes noticeably washed out and pale. Sunsets and sunrises turn unusually orange and deep red as the dust particles scatter incoming sunlight differently than clear air does. The effect is dramatic enough to be visible even to casual observers, and it's also atmospherically significant in ways that go well beyond aesthetics. It's worth explaining the actual physics behind why Saharan dust produces such vivid sunsets, since it's a genuinely useful way to understand what's happening in the atmosphere overhead during one of these events. Sunlight is made up of a full spectrum of colors, and under normal, relatively clean atmospheric conditions, blue light scatters more easily than red or orange light as it passes through the air, which is why clear daytime skies appear blue. When a heavy layer of fine dust particles sits suspended in the atmosphere, those particles scatter and absorb light differently than clean air does, particularly at low sun angles near dawn and dusk, when sunlight has to travel through a much thicker slice of atmosphere to reach an observer's eyes. That longer path length, combined with the dust particles present along it, filters out more of the blue and green wavelengths before they arrive, leaving the reds and oranges to dominate what people actually see. It's the same basic physical principle responsible for unusually vivid sunsets following major volcanic eruptions, just driven by a very different and far more routine atmospheric source, in this particular case. Air quality monitoring stations across the affected islands have been tracking particulate matter concentrations, climbing well above typical baseline levels during the peak of this dust event, with some monitoring sites in Puerto Rico and the Eastern Caribbean Recording Air Quality Index, values reaching into ranges classified as unhealthy for sensitive groups, and in the most concentrated pockets of dust, unhealthy for the general population as well. That's a meaningful public health consideration for a region where respiratory conditions like asthma are already reasonably common, and where many households, particularly in lower income communities, don't have reliable access to air conditioning or indoor air filtration systems capable of meaningfully reducing exposure during a multi-day dust event like this one. From a hurricane forecasting standpoint, this specific combination of Saharan dust and El Niño wind shear is actually working together this summer to produce one of the more storm-suppressive atmospheric setups the Atlantic Basin has seen in recent years. The dust layer itself carries hot, dry air that destabilizes any developing thunderstorm clusters trying to organize beneath it. increasing atmospheric stability in ways that directly prevent the vertical development a tropical system needs in order to strengthen. At the same time, the stronger than normal wind shear generated by this year's El Niño pattern is independently tearing apart any circulation that manages to get started despite the dry air. Together, these two forces, the Saharan air layer and El Niño-driven wind shear, are functioning something like a double lock on tropical development across the main breeding grounds of the Atlantic and Caribbean. The tropical waves are still arriving on schedule. The moisture is technically still present in the wider atmosphere. Ocean water temperatures remain warm enough to support development in principle. But every time one of these systems attempts to organize into something more significant, it runs directly into a wall of dry air, suspended dust, and disruptive wind shear that dismantles its structure before it can build any real strength. This combination explains why the 2026 season has started so quietly, and it also explains why current model guidance isn't picking up significant development from any of the waves currently active in the basin, at least through the early part of August. As the month progresses, conditions are expected to gradually become at least somewhat more favorable for development, as some of the current dust plumes diminish and the surrounding atmosphere slowly moistens back up. But the broader suppression effect driven by this year's El Niño pattern is expected to persist through the traditional peak of hurricane season, meaning August, September, and October. Historically, the most dangerous stretch of months for Caribbean hurricanes are currently forecast to run notably less active than they did during the extended run of hyperactive seasons, stretching from roughly 2017 through 2025. The drought conditions many Caribbean islands have been experiencing this summer are directly connected to this same combination of dust and suppressed tropical wave activity. The rainfall islands, typically received from passing tropical waves during this stretch of the calendar, has been significantly limited, and the dust has effectively cut off what little shower activity those weakened waves were still managing to generate. Several islands have reported dangerously dry conditions as a result. When the dust eventually clears and a healthier tropical wave arrives without a layer of dry air sitting directly on top of it, the resulting rain will likely be genuinely welcome. But in the meantime, the situation has created real difficulty for agriculture and water supply management across multiple island communities that have now been waiting weeks for meaningful rainfall to arrive. The practical impact of that extended dry stretch varies considerably depending on how a given island manages its water supply, its agricultural base, and the resilience of its power grid, since many islands across the region also depend heavily on hydroelectric generation that suffers directly when reservoir levels drop during an extended dry spell like this one. Islands that rely heavily on reservoirs fed primarily by seasonal rainfall rather than groundwater aquifers or desalination capacity tend to feel the effects of an extended dry spell first and most acutely, since reservoir levels can decline noticeably within just a few weeks of below normal rainfall during the warmest part of the year, when evaporation rates are also running at their highest. Agricultural producers across the region, particularly smaller farms growing rain-fed crops rather than irrigated ones, have reported reduced yields and delayed planting schedules tied directly to this summer's persistent dryness. Water utility authorities on several islands have already begun implementing or considering rotating water restrictions in specific municipalities as a precautionary measure, a step that tends to draw far less national and international attention than a hurricane does, despite representing a genuine, ongoing strain on daily life for the households affected by it. From laundry and bathing schedules to small-scale irrigation for home gardens, many families rely on to supplement their food budgets. The third story unfolding across the Caribbean right now is happening entirely underground, and it tends to receive far less attention than tropical weather, despite being, in the long run, equally significant for the safety of millions of people living across the region. The Caribbean sits among the most seismically active zones anywhere in the Western Hemisphere, and the underlying reason is straightforward geology. The Caribbean tectonic plate sits between the North American plate to the north and the South American plate to the south, and the boundaries where those plates interact remain in almost continuous motion along the northern edge of the Caribbean basin. The North American plate moves westward relative to the Caribbean plate at a rate of roughly 20 millimeters per year. That motion isn't smooth or gradual in any meaningful sense. It accumulates as building stress along a network of major transform faults, including the septentrional fault running through northern Hispaniola, the Enriquillo Plantain Garden fault running through southern Haiti, the Oriente fault along the southern edge of Cuba, and the Puerto Rico trench fault system, which lies beneath the ocean floor north of Puerto Rico and the Virgin Islands. This fault network has a documented history of producing some of the most catastrophic earthquakes anywhere in Caribbean history. The 1946 earthquake near the Dominican Republic's Samana region registered at roughly magnitude 8.0 and generated a tsunami that was observed as far away as the New Jersey coastline. The 2010 Haiti earthquake at magnitude 7.0 killed more than 200,000 people, and remains one of the deadliest natural disasters recorded anywhere in the Western Hemisphere. The 2020 magnitude 6.4 earthquake off northwestern Puerto Rico caused significant, well-documented damage across that island. This fault system is not quiet. It has never been quiet, not for any extended stretch of recorded history. It's worth putting the 2010 Haiti earthquake in particular context, since it remains the clearest, most tragic illustration of why this region's earthquake risk deserves ongoing attention rather than being treated as a purely abstract geological fact. That earthquake, at magnitude 7.0, was not, in strict seismic terms, an unusually large event by global standards. Earthquakes of that magnitude occur somewhere on Earth multiple times per year, without producing anywhere near that level of loss of life. What made the Haiti earthquake so catastrophic was the specific combination of a shallow epicenter located extremely close to a densely populated capital city, combined with widespread construction that had not been built to withstand significant seismic loading. That combination, a moderate to strong earthquake striking a dense population center with vulnerable infrastructure, is precisely the scenario seismologists and disaster planners across the wider Caribbean continue to worry about most, since several of the region's major population centers, including parts of the Dominican Republic, Puerto Rico, and other islands along the same fault network, share at least some of those same underlying vulnerabilities. What's happening right now is a cluster of moderate seismic activity concentrated in and around the northern Caribbean. The magnitude 4.5 earthquake that struck near Sánchez in the Saharan province of the Dominican Republic on the morning of August 3rd, 2026, was felt across the Samana Peninsula and in Santo Domingo, and may have been detected in parts of Haiti and Puerto Rico as well, though it caused no reported casualties or structural damage. That specific event didn't occur in isolation. The Dominican Republic has recorded roughly 1,200 earthquakes annually in recent years, according to long-term monitoring data, with dozens each year registering at magnitude 4 or higher. The strongest single event so far in 2026 was a magnitude 5.0 quake near Boca de Yuma at the end of June. Running in parallel with that activity, a separate cluster of earthquakes ranging between roughly magnitude 3 and magnitude 4 has been ongoing in and around Puerto Rico and the U.S. and British Virgin Islands over recent weeks and months. Additional smaller events have also been recorded near St. Lucia and along the Central American coastline, including Nicaragua and Costa Rica, which sit along an entirely different subduction boundary, where the Caribbean plate interacts with the Cocos plate, arriving from the Pacific side. None of these individual events, taken on their own, are catastrophic. A magnitude 4.5 is a genuine, noticeable jolt, strong enough to rattle buildings and understandably frighten people, particularly in areas where local construction standards weren't designed with significant earthquake loading in mind. But it isn't the kind of event that produces widespread structural damage on its own. The real, longer-term concern in this part of the world isn't any single moderate event. It's the accumulated stress that recurring moderate sequences like this one can sometimes indicate is building along fault segments capable of producing much larger ruptures eventually. That concern is grounded in real seismological reasoning, rather than simple anxiety about earthquakes in general. Faults accumulate strain gradually as tectonic plates grind past each other over years and decades, and that strain has to release eventually, either through a series of smaller earthquakes that gradually relieve pressure along a fault segment, or through a single much larger rupture. Once accumulated, stress exceeds what the surrounding rock can hold. Seismologists studying a region like this one pay close attention to which specific fault segments have and haven't ruptured recently, since a segment that has gone a long time without releasing significant strain is generally considered to carry higher, longer-term risk than one that ruptures more frequently in smaller increments. This is genuinely difficult, imprecise science, and it's important to be clear that current seismological understanding does not allow for reliable short-term prediction of exactly when or where a major earthquake will strike, even with detailed knowledge of a fault's overall history and current stress state. The septentrional fault running through northern Hispaniola and the Enriquillo Plantain Garden Fault in southern Haiti are both considered capable, based on their geological history, of generating earthquakes in the magnitude 7.0 to 8.0 range. The Puerto Rico Trench, which lies just north of the island and ranks among the deepest points in the entire Atlantic Ocean, sits above a fault system capable of generating both large earthquakes and dangerous tsunamis. Scientists monitor these faults continuously, using networks of seismometers and GPS stations capable of detecting even millimeter-scale ground movement over time, and the recurring moderate seismicity currently being recorded across this region is generally understood as part of the normal background activity of an actively moving plate boundary, not necessarily a specific warning sign of an imminent larger event, but a persistent, ongoing reminder that this part of the world sits on genuinely unstable ground. and that preparedness matters here as a matter of routine rather than emergency. So stepping back and looking at the Caribbean as a whole during this first week of August 2026, what's actually visible is a region simultaneously managing three separate atmospheric and geological forces, each affecting daily life in a distinct way. The tropical waves are moving through the basin on schedule, but being actively suppressed by this year's strong El Niño pattern combined with the current Saharan dust layer, keeping rainfall below what many drought-stricken islands genuinely need, while also meaningfully lowering the overall hurricane threat compared to several recent, more active years. The dust itself is simultaneously degrading air quality across a wide stretch of the northeastern Caribbean, while further limiting the rainfall the tropical waves would otherwise be delivering. And, beneath Hispaniola, Puerto Rico, and the wider northern Caribbean, the ground continues its persistent seismic restlessness along fault systems with a documented history of producing some of the deadliest earthquakes recorded anywhere in the Western Hemisphere. Each of these three systems operates on its own separate timeline, responds to its own distinct set of drivers, and requires its own specific kind of attention and preparation from the people living underneath all three at once. The El Niño signal currently suppressing hurricane development this year is expected to strengthen further toward a strong or potentially very strong event by late 2026 into 2027. The Saharan dust events will likely continue arriving in pulses throughout the remainder of the summer, with some days clearer than others as individual plumes arrive and gradually dissipate before the next one follows. The seismic activity along the Caribbean plate boundary will continue as it always has, without any currently reliable way to predict exactly when or where the next significant event will actually strike. There's a broader point worth making about why tracking all three of these systems together, rather than covering each one in isolation, the way most day-to-day coverage tends to, actually matters for people living in the region. The community currently dealing with drought stress from the Saharan dust event and reduced tropical rainfall is, in a very direct sense, in a different position to absorb a future hurricane than a community with full reservoirs and healthy agricultural conditions would be. Similarly, a community that has just experienced a moderate earthquake, even one that caused no reported structural damage, may have buildings with hairline damage that isn't immediately visible, but that could make a subsequent hazard. Whether that's a stronger aftershock or a tropical storm's wind and rain, meaningfully more dangerous than it would be on undamaged structures. None of these three systems exist in a vacuum from the others, even though they're driven by entirely separate physical processes, atmospheric circulation on one hand, and tectonic plate movement on the other. The cumulative overlapping stress they place on infrastructure, water supply, agriculture, and public health across the same set of islands is the more complete picture, even when any single week's headlines tend to focus on only one of the three at a time. The most useful thing anyone living in, or simply following this region, can do right now is stay genuinely informed, stay reasonably prepared, and understand clearly that a quieter than average hurricane season is not the same thing as a risk-free one. It only ever takes a single storm to change that calculation entirely. And beneath the surface, across this entire stretch of the Western Hemisphere, the ground never fully rests.